the slideshow?
Yep, looks great.
Okay. Got it. Okay.
Just here in the room.
So, welcome to my presentation and to our presentation, actually, and the things that we have been working for Bridges to Prosperity and what we have been working on for like effectively a year and a half now. So some motivation and some background for the work that we have been doing. The main motivation comes from Bridges to Prosperity and the need to build infrastructure and more specifically trail bridges in various different locations in Africa. To have safe access to critical destinations, as you can see, and through partnership with local governments, take it a step further and actually build those bridges when they deem necessary. Bridges to Prosperity had and still has their own way of identifying trail bridges, and then they would pass it through local municipality and local government in order to assess the location and assess better whether they're going to be available to build them. The main issue that they had prior with us working with them is that it was very time consuming and resource intensive because most of the work that they were doing was being done by hand, and they were identifying bridges in a more like a manual labor kind of a thing before they came on board with us in order to build for them the models that we have already, which I'm going to be talking about. We're still working on building the methodology that I'm going to present to you today, and it's still an ongoing process, but we already have initial results and initial locations that we're sharing with them and that we're sharing with their team in order to train the models that we have and in order to capture more data for future reference. As I said, the objectives are to identify those remote locations using classification models, and specifically we're using Fast AI and ResNet. You will hear about it when I speak about those models, and identify where those trail bridges are going to be, and they need like specific locations, X and Y. And along with those, with that information with X and Y, we also provide them with like F1 value scores that they score the locations based on probability of how high of a probability a bridge would be there or not. Then we also have the team of Bridges to Prosperity that are in Africa, that they're collecting the data for ground truthing and for validation purposes. And our specific goal is to have like develop a model that we would be able to give to them after we're done, and they would be able to either retrain the model with new data or run the existing models that we have on the existing trained data that we have. The main focus, of course, would be to have reproducible code all throughout, and as much as we can have like open source data information, which we have been able to do, so that everything is reproducible and easily handed down to them. So for the methodology, what you see here, sorry, 1 second. What you see here is essentially what the skeleton or the outline of what essentially we would like to give back to them after we have finished all the small parts of this whole structure that you see here. So far, on the upper half of the outline, we have 2 parts that have been divided between us in EarthLab and the upper part that was given to another team, Autodesk, that they were working on. So quickly to touch upon what has been done from Autodesk, they were responsible of creating a multivariate model using different variables in order to make inference on the locations that we have said that we have ground truth information. The outcome of their work would constitute whether the variables that they have used are useful or they were not useful for making inference. The lower part of this tile, you can see where we came in, and we have been trying to create an optical model using satellite imagery and aerial imagery. We have, I will go through both of those because we have used both aerial and satellite imagery. So far, currently, we're using satellite imagery from EU, the EU Copernicus program, Sentinel, and we're using their data, which is of course open source, and we are creating those composite images over long periods of time in order to try and eliminate as much cloud coverage as we can through the region, because clouds will always be a problem when you're trying to make inference on the ground level. We also standardized for the color within and across regions. So these are the initial inputs and the initial data. So the rest of the outline that you see here is based on what we will be giving back to them. So we already have trained the models that we have. So let's say that they have the final product, then whether it will be based on their understanding and whether they would want to retrain a model or not, or maybe use some of the models that we have already there. That's why you see some yeses and nos. So for example, here, if we have previously trained models, and if we already have the composite images of the areas that they're looking for, then that would mean that they can go and get the data down here, clean the data, and have the model make inference on the composite that we have. The other side of the spectrum would be that if we don't have a trained model, or they want to train a new model, then they would of course provide the ground truth information and the ground truth data that they would have. They would create a new initial training sample, and then take the training sample, create the composite, and then retrain a model from start to finish, store the model, and then check the actual accuracies and precisions of the model in order to figure out which one of the models is performing better, which one of the architectures, because ResNet comes with different architectures, so which one of the deep learning architectures is performing the best. This is what you see over here. This would be the whole process of taking a new training sample, creating a new model, having it run throughout, storing the information and storing the necessary weights, perform the analysis of checking the precision of the model, and then pick the one that performs the best. And so on, finalize with having inference on the ground and being actually able to grab the tiles and see that. I'm going to show you what that looks like. The first part of the multivariate model that was created by Autodesk, you can see here some of the variables that they have used, which is OpenStreetMap image of the actual location on the ground. You can see that they use population, elevation, slope, roads, waterways, administrative boundaries. But of course, not all of them were useful for making inference. Highlighted here with green, you can see what of the variables were actually useful on making inference, and that you could gain knowledge out of. This is one of the last parts that I'm going to be working over summer, just to try and incorporate their work with our work in order to have like a unified model. These are some of the results that they have reported back to the Bridges to Prosperity, and you can see that they have used different tile sizes, which is also a recurring thing with the work that we have been doing. And since I mentioned that, it would also be wise to mention that the reason why we're using different tile sizes is that you're capturing different variability with different tile sizes. And based on our model and what we have run so far, if we had a big enough tile, the model would recognize a lot of locations in many tiles. So it wouldn't be very realistic because a lot of the tiles that I'm going to show you in a bit would come back as like, yes, there are bridges everywhere, which is not realistic. So hence, going to smaller tile sizes and finer resolution would capture more variability. Okay, so for the Sentinel, there are a lot of steps that go into the pre-processing before we even train the models and before we even make inference. There are like a lot of steps that we need to take in order to make sure that we get the cleanest or the clearest composite image that we can get. Along with the Sentinel, as you download information from the Sentinel, you download those files that are like compressed 700 megabytes for a day. And it's a 10,000 by 10,000 grid of geotiffs. Within the files, they have themselves identified some locations for some clouds. So we have incorporated all of that into our code in order to download the files, extract the files, identify the shape files that they have identified as clouds, then turn those into NaN values so that essentially we can compute a median without incorporating the NaN values, sorry, excuse me, and disregarding the NaN values and getting a median over a specific period. So far, we have been running for different areas. We have been running for up to 6 months of a period. And then we take all the different periods and we compile them together. You can imagine a 10,000 by 10,000 grids all stacked on top of each other. And then we're grabbing a median value for each of the pixels of the 10 by 10,000 over a long period of time. Of course, we had many problems working with Google Colab. Which I'm going to mention briefly because of timing errors and running out of memory, and because those composites can get like really memory intensive, and hence we would run out of memory online and the whole code would crash when you wanted it to run for 10 hours, for example. So far, we have already trained for 600 meter tiles, but we found out that it's not realistic and it's not as good of a model when we went down to 300 meter tile, and that's what we're working with now. And the main focus will be to run threshold analysis in order to figure out when you're comparing the trained model versus the validation model, and figure out what is a good threshold to start picking F1 values with a certain probability and saying that we're kind of certain that these locations would work as being locations for trail bridges. And I will show you how the thresholds look and how the tiles look all together. So for the results. What you see here is mostly referring to the initial work that we were doing using Microsoft API. We went down that route because, to begin with, it was easier to capture images from Microsoft's Bing API, giving X and Y locations, and we would use their API and we would download a lot of images and we would make inference on the images themselves. It turns out, though, that the images that we were downloading from Microsoft, they had no metadata. They were compiled from what they were saying on their documentation online, that they would be compiled within the 10-year period. So nothing much given beyond that information. So you wouldn't necessarily know what period it was, what time of the year the aerial imagery was captured, and so on. And frankly speaking, some locations, they just didn't even have imagery at all. So there was like empty no images that would be downloaded, like no data images that would be downloaded, and that would also be another problem that we would have. What you see here at the beginning was our focus on the 3 different zoom levels of the images that were being downloaded. After running our initial models, we found out that images of level zoom 17 and 16, which correspond to this resolution that you see up to the right. 17 actually was not the best, so we ended up working with 15, 16. But from then on, we moved and we scrapped Microsoft Bing imagery because it was just like not usable. So also considering that maybe some of the work will be published, it's not the best when you're downloading and you're using all those images that have no metadata and that you cannot really report back to. Like, yes, the input was there and the Microsoft imagery would be useful, but unfortunately, the information would not be enough in order to be reproducible even. So these are some of the initial curves that the trained models showed with Microsoft Bing imagery, and you can see like they have high precision and recall for both yes and no. When you see yes and no, is like yes breeds, yes locations, and no locations. So although there were high precision and recall, and the models seem to be doing fine. Of course, when it came down to the actual, validation, because we ran another validation, manual validation with a team in Africa, they saw that the actual precision was not that high, and I will talk about it later. This is some of the initial results that you see here. Is the inference that was made using Microsoft. So then we trained the model, and then we took the model and we took the tiles over a whole area. If I'm not mistaken, this is RC, West RC, I don't remember. So we took the model and we ran inference on the whole area, and we asked the model to identify whether each of the tiles were yes or no bricks. And this is essentially what you see here on the left. You see all of the values. You see F1 values, of course. This is the classification that you see down here. The higher the the higher the F1 value, the greater the probability is for whether there's going to be breeds there or not. And you can immediately see, well, not immediately, but after seeing so many outputs between the team and between us, you can start seeing that there is this artificial striping that was happening with the initial models that we trained on Microsoft's Bing API. And you can see that there is this striping of, there is like yes bridges all over this stripe going north to south. And you can see it in both images here. So this striping was one of the initial concerns that we have, that something artificial is happening in the background that is kind of like not capturing a realistic scenario. And that is essentially what drove us away from Microsoft Bing API, and we went towards Sentinel. This is what I was talking about earlier about the threshold. We took different samples from the training and the validation, and we made sure that the F1 values were correlated and they were matching. So you can see here that at some point the training data starts kind of lower F1 values, and then it picks up, and then it surpasses the inference data that we had. So for an example, we picked that threshold to say that whatever was above that threshold we would use, because both of the validation and the training data models were in agreement, and they would say that they were both certain that those locations would be a yes location for a bridge. And this is what you see here after applying the threshold and picking those specific locations that were above the thresholds that I just talked to you about. And you can still see here that there is still striping. So the problem remained. Of course, there would still be striping because it came from the initial inference data. So the problem remained, and that pushed us towards Sentinel. This is also what I was saying earlier. You can see that this is the actual accuracy that the team in Africa reported back to us after we applied the threshold and we gave them those locations, and they manually sat down and actually reported whether the locations that we gave them were true or they were not. And the accuracy was way less. So moving on, we started experimenting and working with Sentinel. Now, Sentinel is unique. What they have is this product that they have mapped out the whole world with those unique codes that you see here. All of these unique codes are essentially referring to a 10,000 by 10,000 grid. So you can imagine that one of these codes would be like a rectangle of 10,000 and 10,000, and then another rectangle. So essentially they have tiled the whole world. So initially what we do, we have an area of interest, as you can see here. We get the bounding coordinates of the shapefile. We identify the unique codes that cover that location based on the whole tiles that they have for the whole world. And then given those tiles here, for example, for this area here, you would have NRA, NTF, MRV, excuse me. So for those unique identified tiles, we would go in and we would ask from the API to download X amount of period of time, and then take it from there and download all the necessary information and start extracting and trying to create a composite. What you see here on the right is just some of the training samples that we had, and this is why we focused, for example, on this area. This is how one of the composites would look like from the satellite imagery. And this is exactly one of the tiles that I was talking about. This is as big, and actually these are two tiles, excuse me. So you can see NTF and NTG on top of it. So you can see how they separate over here. And then this is the outcome of some of the composites that we would have. Now, talking back to what I said about the clouds, this is some of the shape files that come along with the downloaded folders. So they have a specific folder structure in there, and we have excuse me, we have written the code in a way that it goes in a specific file. It checks if that file has a specific size, because that would tell us that we actually have some clouds in there. If it has, then we go into the 10,000 by 10,000, we geolocate where that cloud, the shapefile would be, and we drop all the cloud data that we have as NAN values, so that we don't measure them on the final median composite image. So these are just a couple of the examples of how the cloud coverage would look like over the area and the downloaded Sentinel files that we had. These are some of the grayscale examples of the Sentinel images that we had, and you can see that they're not perfect themselves, of course, and they have a lot of cloud coverage. You can barely see some of the water underneath it. The reason why I'm showing you this is because it's like the initial step when you download them, and of course it's grayscale. But the good thing about Sentinel is that you can specify different time of the year that you can download. You can specify different years. You can have a composite of many years, none of which was available for us using Microsoft Bing API. So this is one of the problems that we encountered. What you see here on the left is the way we came up with a solution in order to keep our code running in Google Colab for up to, I don't remember, 10 hours and so on, and be able to actually not to run out of memory. So if you take the whole composite and you read it into memory and try to take a median out of several different composites, you will find out that Google Colab runs out of memory very fast. So our solution to that was that we read the composites, or we read the initial Sentinel images in stripes, and that's what you see here. So you see one stripe of X and Y size and another stripe of a different size. So the more images that we downloaded, the smaller the stripe had to be in order not to run out of memory. So it was kind of like a balance. And we're talking about code that has to be running constantly 24/7. So whenever something would break down, it wouldn't be a big waste, but we had to find a way around it. So that's hence why we started doing the striping that you see here. And then we take stripe here, stripe, 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 and we take all the different stripes and compile them back together into a single composite and write the composite into memory and finish the procedure, which is quite timely sometimes. So yeah, so that helped a lot. What you see here also is that we have applied our own white threshold, pixel value threshold, in order to get a cleaner image. So I don't know if you can tell. Yeah, you can probably tell. So this is a threshold of 6,500. So everything above 6,500, we would turn into NaN, and we would drop it from the composite as a value. This is above whatever was above 6,000 would be dropped, whatever was above 5,000, and so on. And you can see, focus on the right side of the image. Starting over here, you can see how this embankment or the river trail, you can see how it becomes cleaner and cleaner as we go to a lower threshold. And this is what also is written inside the code so that it can help us, other than the save files and the cloud save files that we have. This is another step that is making safe proof that we can get as clean image, as a clean of an image as we can get. From then on, what you see here is one of the composites that we had. And in order to train our initial data, we had to actually create our own tiles, which is what you see here, because the training samples would be scattered all around the composite. So we had, so we had to find a way to create small tiles and small square buffers around it, and extract only the information that were falling within the tiles in order to create our trained sample sets and do the training. And this is actually what you can see here. So you can see how randomly sometimes, which is realistic, a realistic scenario, how randomly the sample points, the training sample points would fall within the tile. You wouldn't expect that the sample points would fall square in the middle, in the center every single time. Then that's what you see here, the representation of a realistic scenario of what would go into a training data set. And these are just some of the initial outputs that we were showing based on the ground truth information, and with, of course, the F1 values. And it took some more writing code from turning to single points and turning them into tiles again, because we had to start from the beginning. And this is just some of the areas and some of the different locations that we have made inference. For some of the initial passes that we had, one of the problems that we have solved as well was what I mentioned earlier with normalizing the colors and the color spectrum within different regions and across different regions, and normalizing the pixel values so that they all fall within the same range. Before we did that, we had some artificial stuff happening here that you can see, like a lot of the yeses were in one side, although you still had some no's, and a lot of the no's were in one side. So that was one of the things that we solved with normalizing across different regions and normalizing the pixel values. And these are the trained models of the Sentinel. And if we go back to the previous table that we had from Bing API, you can see that this is outperforming that, but we yet still have to check with the team there and do another validation run for them that they will also do for us, so that they can manually do some of the work that we have been giving them. Yeah, this is one of the results. Excuse me. This is one of the results that you see here. This is the Sentinel. So the thing that makes us really happy is that there's no more striping. Oh, sorry, excuse me. There's no more striping, meaning that you don't see the striping that you would see with Microsoft Bing, that it would be like a yes kind of a trail north to south. This is how it should look like. One of the things that I want to tell you is that this is you don't see the whole area covered, because just there was simply not enough time for the code to finish, and it just ran out of time. That's why you see like you see a line over here, and you see the whole tile over here. This should be like the whole image, right? The inference for the whole image, but this is what we had time for without Google Colab crashing on us. Anyway, so this is what you see as an output from Sentinel along with tiles. This is something that we would give to the team after applying a threshold for these ones, and that we would give to the Bridges to Prosperity so that they would go actually on the ground, check some of those locations, and see if the model is true to its inference. And this is one of the new thresholds that we have applied for one of the models that we have picked for the Sentinel imagery. And a new threshold of 0.34 was applied, and it would be applied to these tiles so that we can pick some of the tiles only and just give them that. Of course, we will not give them like thousands of tiles because they don't need thousands of tiles, and some of them don't need to be a bridge to begin with. That's why we need to drop down the number of inference tiles that we would have. Currently, we are focusing on one of the more challenging areas in San Pedro in Côte d'Ivoire, because the team of Bridges to Prosperity is going to be there by the end of June, and they will train, according to my understanding, they will train new people of how this whole process is working. And what you see here is the area of San Pedro, and what Natasha sometimes says, the pesky clouds. They are quite pesky because that area is kind of like cloudy all the time. There are 2 months or 3 3 months of low cloud coverage, but then we're still trying to run it through many months of X and Y years so that we can get a cleaner image. But for now, this is what we have been working with, a 6-month period of 2 years. And the next steps would be, as I said, to unify the two models that we have, to unify the multivariate along with the optical model that we have, to of course optimize the code as much as we can, because we need it to be running we need it to be running 24/7, because it can run 24/7 and it can make inference for huge areas, and we can use that, and they can use that, and they can have it running on a server. But first we need to optimize it to run on a server, and there is like this transition that is happening currently, that we're trying to move away from Google Colab and focus on running it in AWS and running it constantly for different countries and different regions. And so that like a lot of the time through my day, I have to sit here and baby the model in order to make sure that it doesn't stop, in order to make sure that it keeps on going. So we need to, excuse me, move away from that. And of course, we have a few more things that we need to check, and we have to be certain about the tile size, whether we're going to go on a lower tile size or keep it at 300 meter by 300 meter. We have to check for the confidence threshold again. And yeah, so for just some open questions that we have, there are still some clouds remaining, as you can see, and some haze. But we have worked so much with the composites, and we have written so much code for that, we're happy to report that it's actually working, and it's actually working fine. And we have to keep in mind that the locations that we're working are very highly cloud covered throughout the year. So if we see a kind of a clean image coming out of that gives us like more confidence that these things are working and everything is working fine. So, and we're still, and also another thing that I didn't mention is that some of the ground truth information that we have from the team of Bridges to Prosperity, they not only are in cloudy areas, but there are also on high elevation areas, which they both kind of combine into making it kind of a more difficult approach. And of course, you have snow coverage. That's why the white gauge threshold that we are applying cannot be too low, because we don't want to necessarily eliminate everything. So yes, so this is more or less what this project has been doing the last year. And thank you for attending, and please ask some questions if you have any.
So if you want to clap again.
I think I just saw it. There was no audio, but I saw it.
Hey, George, do you want to go out of presentation mode to full screen so we can see you?
Yes.
Awesome. Thanks so much, George. That was a really good overview. Does anybody have any questions, George?
What is your intuition as to why you were getting the striping with the big data? Because that seems like really weird.
Yeah, so I don't, well, I think I have one open. One of the things that I also wanted to show was this. So this is one of the images that we had from Microsoft Bing, as you can see. Of course, there is a cloud there. There is nothing we can do about it. The cloud, like, there's nothing we can do about it as we can with the Sentinel images. So the image would come down as this, and we would actually use some of those images that had clouds, and we would train the model. So, so my intuition would be that just that the images were not that good, that they had clouds, and they were like, some of them no data, and we tried to filter all of it out, but the cloud images were still there. So my intuition would be that just that the input was kind of like not as refined for the initial models that we trained, and that's why the model was giving us this striping and this artificial striping that I showed you on the earlier slide.
And just to add to that, there's when they collect the imagery, even if it's airborne or satellite, they fly on an orbit track. And so that orbit track follows, you know, a straight-ish line. And the problem is there's no metadata to see what that orbit track is or to correct for it.
Exactly, thank you.
So one thing that George has been doing that's really amazing is he's been doing everything programmatically to scale out. So it's not just like, oh, how do we do this over a study area, but how do we do this so they can run it over any country, let's say in Africa. And Bridges to Prosperity has been so happy with the work that George has been doing to generalize that they've even talked about, oh, well, what about Southeast Asia? Can we go to Southeast Asia? So they have really big ambitions for the work that George has been doing, and he's been really trying to make programmatic decisions.
And we can actually do that. We have everything we need. We just like need an initial shape file of somewhere in the world, and then we can start downloading Sentinel images, and then we need some sort of ground truth information to train models, and then there we have it. Or we can use the models that we have and make inference somewhere else in the world.
Has your result been used at all yet in infrastructure decisions?
That I do not know. I do not know that. Maybe Natasha knows, but I don't know if they have actually used it. I don't know what's actually happening past that point.
So our big first test is this Friday. So that Cote d'Ivoire, like you guys are really seeing everything in real time. That Cote d'Ivoire, we're giving to them inference for Friday. And that will be their first time where we say, hey, we think there's a bridge here, and they're gonna go there and say, yes or no, we actually think there should be a bridge here in their training. And then they're gonna do that throughout the summer. And we have 5 different countries they want us to do it in as they do their field campaign this summer. But the plan is not to replace human in the loop decision making with artificial intelligence, but how do we use the artificial intelligence to help them in deciding where to go, and then they create a report that they then give to governments, and then governments decide to make investments.
Right.
So we're a small piece of a bigger, much bigger decision framework.
A question. Yeah. So why did you choose ResNet particularly as your model infrastructure?
Well, to tell you the truth, the initial decision didn't come from me. I got when I started working on that, there was already a decision made that they were working with ResNet. But but beyond that, it's one of the more well-documented libraries that works extremely well in Python with many examples on different data sets. So my understanding to begin with was that we wanted something that is reproducible easily, and that you already have examples and you already have some code and you don't start from scratch. So provided that that library was easily available to us, I think it was just like a wise decision to go for that, and just the easiness of working with it. It's like although it's deep learning and there's like a lot of things happening under the hood, as they're always saying about deep learning, you can have a lot of documentation online to actually guide you through a lot of the steps that you need to. So I think that's why we went down that route.
All right, well, I think doesn't look like, are there any other questions in the room? Okay, well, George, thanks so much for presenting on your work mid-work.